Okay. Okay, so I'm going to talk about simplifying programming distributed cyber-physical systems through a separation of concerns. Cyber-physical systems are everywhere around us, and more recently they have been used in arenas such as, aside from the expected traffic and autonomous driving, they're around us in medical supply deliveries, entertainment industry, with several applications such as distributed tasks, formation flights, and warehousing applications. What does it take to program a cyber physical system? So let me demonstrate by, this kind of, I'm not sure if something is blocking the top of the screen. Can you guys see the distributed task application app
Yes,
title?
I see the whole slide.
Yes.
Okay. Yeah, because it's being blocked in my screen. So I'll demonstrate through an example application. So here's a distributed task allocation problem. So given a set of possibly heterogeneous robots, there's a fixed set of tasks that they have to do, and we can see tasks as abstractions for delivery or mapping or surveillance, given a safety distance that each robot has to maintain. The objective is to design an application such that every unvisited task in the sequence of these points is visited exactly once by each robot, and no robots ever get closer than epsilon. Let's look at an intuitive way to design this application. So we start with looking at a car. The car finds out whether or not there is a task available. If a task is available, then it checks if there's a clear path to that task. If not, then it looks at all other available tasks, checks if there's a clear path. If yes, then it shares its current path and then follows it. This whole thing can be captured as an assignment event where a task is being assigned to a vehicle, it's sharing and following a path. And once it reaches, it completes the task, and this entire process goes on until all the tasks are completed. So this is a pretty intuitive way, but how do we capture this nice intuitive formulation in code? So the design is pretty simple, and it can be seen as almost like a hybrid automaton representation, where you pick a task. If there's a clear path, you share and follow path. If you've reached the current task, repeat the process. How do we translate this design to code, and how do we know that the code that we generated for this design is correct? So on the right side of the screen, you can actually see a snippet of the code that we used in deploying this task application, but there is no way to tell what part of the design this code actually corresponds to. And we don't want the user to be burdened with this. The second problem is debugging this application, because there are so many sources of error. So it involves distributed coordination in checking whether or not the tasks are applicable. And one of the concepts required is mutual exclusion, which can be a source of error. There's motion control, which involves sensing and path planning during checking if there is a path that exists, and sensing whether or not a robot has reached a current task. And there's networking, where the agents are sharing and following paths. So the following path involves actuation and control, and sharing involves communication. So all of these can be sources of errors. To isolate these these errors is also a major uh, is a major issue that we're looking at. So first, I'll now give you a tour of CyPhyHouse and Quad. So CyPhyHouse is a toolchain that we designed to simplify the programming of multi-robot systems. We provide a high-level language called Quad, which comes with a compiler, a middleware which supports the implementation. We also provide a simulator and then interfaces to deploy it on actual hardware. Some of the contributions in this project were identifying abstraction for a language to separate the platform dependent and independent concerns, and developing the formal executable semantics using K. I'll talk a little bit about this. We implemented the language and its associated tools in the CyPhyHouse toolchain. And we developed a verification approach and tools using several formal assumptions, proof obligations, and guarantees. And this is an inductive approach, and I'll also touch upon this in the later part of the talk. Some of the other research that is not directly a part of this project is verification of self-stabilizing distributed algorithms. And we're also looking at tools for runtime monitoring using this toolchain and the language semantics. So the first selling point of our language is that it's concise and short. The task application that I showed you, the full implementation in our language is only 50 lines. Shared memory is an intuitive abstraction for communication between robots, so we provide syntax for that. In the task application, we share the list of tasks, status of the tasks, and the shared paths of all the robots are shared as well. The interactions with the environment are simplified through port abstraction. So we use port variables, sensor and actuator variables, sensors such as what is the current position of the car, whether or not the vehicle has reached the location of the tasks, and actuators which set, for instance, in this application, the path that the vehicle has to follow to the task. Any questions so far? Okay. There's also a lot of flexibility that the programmers are allowed in terms of plug and play implementation of path planners, and with other environment interaction modules, there can be other plug and play functions as well. Planning algorithm for the task application. One of the main features that we provide is portability. We can change a configuration file and no change in code to allow for simulating different scenarios. The task application is being simulated on the right side of the screen with 5 quadcopters and 3 cars. The gray points are unassigned tasks. The red points are when the tasks are assigned, and they turn green when the vehicle reaches the task. And the vehicle dynamics might not be the same as the ones that are in actual deployment. In this simulation, they weren't. So this is a video of the actual hardware deployment. We annotated the video with the same legend. The gray tasks are unassigned, the red tasks are assigned, and they turn green when the vehicle reaches. And on the left corner of the screen, you can also see a visualization of the execution in Gazebo. The same code is running on both the quadcopters and cars. I will not go into detail about the actual vehicles, but the drone was, the quadcopter is an off-the-shelf quadcopter, which is running a ArduPilot controller, and the car is running an MPC controller, which was designed in-house by some of our team members. So the motivation behind this project is that the typical development cycle for robotics applications, and I found this out by talking to professors and graduate students, typically with the existing tools, it takes graduate students at least weeks or months to set up the infrastructure and design their application down to deployment, typically a period of 6 months and more. With CyPhyHouse, the aim is to shrink it to days and hours, and our experience has indicated that this might indeed be the case. So now, having given you that tour, I'm going to talk a little bit about my research on formal semantics and analysis of programs using CORD, which is the language for CyPhyHouse applications. So our major motivation for the language design was actually the separation of concerns for design, development, and engineering. So the primary stakeholder is the programmer who writes a code program and then has two major concerns. One is to look at the correctness of the program, and the other is to actually simulate or deploy it. So they use the code compiler to simulate it or deploy it on hardware platforms. But that's obviously not the full system. So if they should choose to prove it, they send it through our code symbolic execution engine. I'll leave that as a term for now, which goes through the code prover to potentially produce a proof. There are a couple of missing pieces here. One is the designer and the requirement engineer who provides the requirement for the safety of the program. So in the task application, for instance, the safety property that we want to verify is that the robots don't come closer than an epsilon distance. The other stakeholder is the platform engineer who provides the assumptions on the hardware platforms or the physics models that also are fed to the prover. They're also important in the hardware problems and the simulators, and can be and the deployment and experiments from the deployment and simulation can be used to refine these assumptions as well. And given all of this, the programmer can finally come up with a proof for their code program. Some of the runtime system assumptions are also important here. The main ones are that each robot in the code runtime system has a unique identifier. Each robot is aware of the number of participating robots and also the set of participating robots. And each of the robots runs an instance of a code application. Okay, any questions so far or any comments?
Right.
Okay. So what does a code program entail? A code program has a collection of events that are specified by preconditions and effects. So assignment event, if the robot is on task. If the robot is not on task, then it tries to assign an event. Completion event, if the robot is currently doing the task and it has reached its position, then the task is complete. The program interacts with the environment using sensor and actuator ports, as I mentioned earlier. And allows each agent to execute at most one event every some delta greater than 0 time units. So I'll make that a little more clear as the talk goes on. So let's look at agent evolution. So each agent executes a set of statements where it can set its root, it can write to shared variables, do some computational components. Based on that, it sets its actuators and then follows some dynamics, which in the task application drive it to the location of task 2. So agent evolution can be broadly broken up into these two components. We use this as state information to build configuration, which specifies the language semantics. And and that is something that I've developed, the language semantics for this language. So what does a configuration contain? There are agent configuration, which, when seen in the context of the previous slide, include something called turn. A turn can either be program or environment. So when a car is executing statements, it's in the program turn, and when it's interacting with the environment, it's in the environment turn. The agent configuration also includes sensor and actuator values and local memory, which is a key value store of maps of variables to their values. These agent configurations are part of the system configuration, which includes a notion of time and the turn of a system, which essentially, because of the way that we've modeled the system, all the agents are either doing a program transition or an environment transition. So the system turn means indicates what is the turn of all the agents, or what is the turn of all, uh, whether it's a program or environment. And the system and configuration also contains global memory. The main takeaway from this is that we need all of these variables, key value stores, and information to specify how the system evolves. Yeah. So Cord comes with a lot of features such as shared memory for communication. We implemented shared memory through UDP-based message passing over Wi-Fi. And any shared memory update translates to an update message. And in our experiments, we looked at a single network node. And mutual exclusion, we also provide mutual exclusion. And we are able to provide plug and play implementations, which is something that most platforms don't. So we tested our implementation for broadcast and P2P models for UDP-based messaging. We implemented port abstractions through abstract classes called motion automata, which has to be implemented for each hardware model. It describes to the required, it subscribes to the required ROS topics, positioning information, for instance, provides the user the plug and play implementations of path planners. So for our applications, we used different types of path planners which had different performances. And these were RRT-based path planners with and without smoothing on the current slide. We also provide support for heterogeneity, which is one of our main design motivations as well. We can deploy or simulate the same Cord program while changing only a configuration file, which looks something like this, contains some robot information, ROS topic information, and some system information. We have also designed our system in a way that will support new port abstraction instances, such as we added a LiDAR support in simulation within an afternoon. And it had the same structure as the motion modules shown earlier. We also have a simulator, which has the same communication interface as the hardware and simulates in Gazebo. And we have different physical models for different platforms, and they run directly in the simulator. We can test different scenarios with, again, the same application code. I'll show a couple more videos of some experiments that we did. This is a formation application that we ran. Basically, a bunch of robots decide to form a shape in 3D, and it's around 5 lines of code. And here is a mapping application also developed within our framework, where 2 robots collaboratively form a map of a space with some static obstacles. So this is part that I don't know if I'm going to talk about, but I'll probably skip this. We provide a tool chain to faster implementation, online monitoring, and potentially live programming of robots. We provide a formal executable semantics for language that has a high amount of extensibility for distributed cyber physical systems. And we identified programming abstraction for separation of platform agnostic and platform dependent concerns. And in general, the CyPhyHouse middleware increases the programmability of these applications. I'd like to thank my collaborators for this project, and please check us out on these links.